Okay, so today we're starting a new topic. Today's topic is operational amplifier from chapter 5. So at the beginning, we are going to introduce the operational amplifier and to explain what is the purpose of this device. And then we are going to talk about some of the applications or circuits that this op-amp is used in. And then we're going to solve some examples, and we will see how we can analyze or apply the analyses that we have learned earlier in this course on those devices. So what is the operational amplifier? Briefly, the operational amplifier is an active device. It's an electronic circuit that is built of transistors in a big box that we don't see what is inside, except we know how is the uh, operation amplifier is symbolized here. This is the symbol for the operation amplifier. It's a triangle, and in this triangle we have the following, that is, the most important pins that are clear for us, which are the input. It has an input, this V1 and V2, such that one of them is more positive than the other one. And it has an output V naught here. Okay. Now, this Ri, we call it the input resistance for this power amplifier. R naught is the output, and it is, as you can see, voltage controlled voltage source. So by itself, it needs a signal at the input in order to generate. It has its own power supply, but it does not generate anything unless you apply a signal at its input that will allow it to sense. And then based on the concept of the dependent source, it's going to depend on that signal to generate a replica of that signal. Okay, so this is in general. So what is the purpose? The purpose for this amplifier, as from the name of it, is to amplify the signal. This is one of the applications, to amplify. It also does mathematical operations on our signal, and that's why we call it. It does signal processing on the analog signal. We call it analog because it is a signal that varies with time, a continuous signal. So it's an analog signal. This operation amplifier can perform mathematical operations, as we will see later on, using using the op-amp circuit. So there are different types of op-amps. We have what's called inverting op-amp or non-inverting amplifier. This is some of the mathematical operation. It does summing, where it adds two signals, two analog signals. It does difference as well. And we can, with the features of the operation amplifier, as we will talk about it, we can cascade several of those circuits, stages together to get the signal that we want. Okay, so now let's go back to our operational amplifier. As I said, it is an integrated circuit with its simplest package, as you can see here. That's a chip that has 8 pins. So we have here, as I said, the output. We have the input that is connected to the negative sign. We call it inverting because it does invert the signal from a positive to a negative. So we call it inverting, or it's the one that will be subtracted. Or the non-inverting, which is connected to the positive sign here, the plus. So this is non-inverting. So the signal will maintain its value as a positive value, or if it's a negative value. And then we have the power supply for the operational amplifier, which is pin number 7 for that package. Pin number 7 here, we have the V plus, which is the positive, and we have the V minus here, which means at pin number 4, which is the negative. So why do we have a positive, negative? We have a positive, negative power supply to the operation amplifier because we may expect our signal to vary between a positive and a negative range, right? So in order to reproduce the signal, it makes sense that my operation amplifier also operates with a positive negative. So my signal, when this signal is being amplified, for example, it will be amplified with the same shape. So it has positive negative. So the output signal would also have a positive negative, but amplified. Amplified within a specific range. We'll talk about that. But that's why we do have an option of having a negative, positive. Not mandatory, but we can have a positive and a negative power supply to the operation amplifier. The pin 5 and pin 1, they're called offset null. They're used to adjust the output of the amplifier such that it eliminates any offset between the two applied signal here in the when we calibrate this operation amplifier to eliminate any offset. Okay, so as I said, on our operation amplifier, pin number 7 is the one that is connected to the positive. And you can see here, this is the VCC. The positive terminal is connected to the pin 7. And then I have here at the negative as the ground. And then I have another VCC. So this is my reference is right here. This is the 0 volt right here. VCC here is going to create a positive VCC right here. And again, based on the definition of the voltage source, this means that if I fix the positive terminal at 0 volt for this one, this means the VCC, this voltage source is going to generate a voltage difference of VCC. But since the positive terminal is fixed at 0 volt, then definitely the negative one will be less. That's why this is going to be minus VCC. So this is how I created a positive negative range of power supply. And as you can see, both are VCC in magnitude, which means that they're equal. But one of them goes to the positive, which is the pin 7, and the second one goes to the negative input power supply, which is pin number 4. The remaining ones, as I said, the most important one that we look or we hook in our circuits. So those ones, the power supply, we always assume that they're already connected. Otherwise, the operation amplifier is not going to work. So this is the power supply that makes this operation amplifier work. Without supplying those power to pin 7 and pin 4, the operation amplifier is not going to operate, not going to work. Okay, so keep in mind that this operational amplifier is restricted by those those supplies, which means when this operation amplifier, let's say, amplify a signal, he cannot go beyond positive VCC or less than minus VCC. So those are his limit. Those are his limit. He cannot go beyond them. He cannot generate power from nothingness. He relies on what you supply to him in order to operate. So he cannot give you a voltage at the output that is greater than VCC. He cannot give you a voltage at the output that is less than minus VCC. So keep this in mind. This is the range that this operation amplifier plays within. So as I said, that operation amplifier that has the positive, negative. The positive, as I said, we called it non-inverting. The negative, we called it inverting. And then this is the V naught. In this case, in this orientation, this is what we call an open loop. As you can see, there is no wiring between the output and the input, and this is what we call the open loop. In this case, the operation amplifier has what's called the open loop gain. And this open loop gain, A, ideally is infinity. Practically, it is not infinity. It may range between 10 to the power 5 and 10 to the power 8. That's the gain. However, ideally, A is infinity. But so here, the difference here between V2 and V1, we call it VD, which is, in this case, as you can see, VD is the difference between V2 and VU1. And that's why we call this one, this is the positive, this is the negative. So we're looking at the difference between those two input. So as I said, this is A, that is the gain, which basically this means that whatever voltage you have at the difference of the voltage you have at the input is going to be amplified by the gain here in this topology, which is A, right? So V naught equals to A times VD, or V2 minus V1. Now, ideally, we will be looking at, yes, go ahead.
So is V1 or V2 the input in this case? So
Yes,
no, which one is which?
both of them. You can look at them as you're taking the difference, because here we have inside what's called the input resistance, Ri. So you're looking here at the difference between those two voltages. So the voltage drop across this Ri, which is basically the difference between V2 and V1. So this is your input.
So both are inputs, and what comes out of and V naught is the output.
And V naught is the output. But keep in mind, so this is the topology of the open loop. We have not talked yet about the usefulness of the open loop with other topologies. So we're coming to this. But right now we are explaining the the concept of the operation amplifier. It is a block that is symbolized by this triangle. It has two input. One of them is called positive, non-inverting, and the second one is called inverting input, right? That are connected between an input resistance that is called Ri. This Ri is extremely high, which means that the current going into this Ri is very small. And we'll talk about the usefulness of this.
So what does it mean to be non-inverting and inverting?
Okay, so it's a differential. It's a differential input. It takes the difference between both inputs. So you have one of them as oriented as a positive. Remember, the operational amplifier, as I said here, we have not, yeah, here, as you can see, is a voltage controlled voltage source. which means that based on the direction of the current, so here, based on the direction of the current, which is in this way, this VDD is going now to generate a voltage, right? So what defines the direction is the voltage controlled voltage source. How is it constrained to the RI? In this case, the current going from this way, going up this way, is basically the orientation that's going to generate a voltage drop here as AVD. So this is what defines the orientation of the voltage of this voltage controlled voltage source. So this current is the one that is, as you can see here, going in this direction, and this is going to result into a VD with this orientation. And now the voltage generated here is based on this. Is this clear?
In this case, V2 is the positive voltage.
That's correct.
Okay.
V2 is the positive, V1 is the negative, and this is what we also have here. But here we're looking at the operation amplifier being flipped. So here we have the V2 up and the V1 down. So don't let this one confuse you. You may see the operational amplifier uh, plus minus like this. And in this case, this one would be V2, this one would be V1. Or you may see the operation amplifier. It depends how is it connected, like this. But in this case, this one is V2 and this one is V1. So this is only an orientation that is drawn for convenience, not more than that. AVD is the voltage that is basically generated by this dependent source. So the whole thing makes the operational amplifier. The whole block is the operational amplifier that has inside the also what we call R naught, which is the output resistance that is very small, and we have the Ri, which is the input resistance, which is extremely high. Okay, so the whole thing is called the operational amplifier, the op amp. What about the circuit in the next slide? Are you talking this one? Which circuit? This is the, as I said, this is the operational amplifier. Here, the operational amplifier is, we're not seeing what's inside this triangle, this black box. We are not seeing here. We're only seeing the pins of the input, this one, and the power supplies and the output. Okay, so here what we have is based on this, number 2 is the inverting, number 3 is the non-inverting. So if we come here, number 2 is the inverting, so this one would be the minus. Number 3 is the non-inverting, this one would be the positive. So you can, if you want, call this one V1 or call this one V2. And as we'll see later on, we also call this one sometimes the V minus, and we call this one the V with a plus, like this, to identify which one, that this one is the inverting and this one is the non-inverting. Any questions so far? Is everything clear so far? Okay. So As I said, ideally we will treat this gain as an infinite gain. We will treat this input impedance also as an infinite ohm, infinite resistance of infinite ohm. The output resistance as a 0 ohm. This is ideally. Practically, no. You can see the ranges for the gain, for the input resistance, and for the output resistance.
Sure.
Yes,
So when with an op amp, we have a positive and negative voltage as an input, and we're trying to make the initial resistance basically infinite. But we're trying, what an op amp does is it takes a difference in that to create a very high voltage.
yes,
Okay.
yes. So this is based on the op amp open loop operational amplifier. The operational amplifier, sense what is the voltage difference at its input, such that it is V, this VD is V2 minus V1, and it amplifies it and puts it at the output, right? But keep in mind that although this amplification is so high, the operation amplifier cannot exceed his maximum or minimum voltage supply, right? So it will reach to a point where it will be clipped and becomes constant. So this is again the open loop topology. Ideally, it senses the voltage at the input of its operation amplifier, multiply it by the gain, and put it at the output. This is ideally. Now we will see that this is a bit restricted, and we don't prefer using the open loop topology in operation amplifier, and that's why we tend to decrease this gain, have a control on the gain, because ideally this gain can be infinity. However, there is a con here when it comes to having an extremely high gain. You will be limited, very limited, and restricted in terms of the frequency bandwidth, the bandwidth used in this operational amplifier. So that's why we tend to use the feedback. The feedback is going to have more control on the gain, bring the gain down, and at the same time increase the frequency response or the frequency bandwidth of operation for this op amp. So we always use the negative feedback, and we'll talk about that shortly. The negative feedback, which is basically having the output reconnected into the inverting input of the operational amplifier, right? So this is how we do it. This is the negative feedback by having the output connected to the inverting input of the operational amplifier. This is going to give me a stable operation where I can have a control on the gain and at the same time make use of increase the frequency, the frequency bandwidth of my operations. So the useful feedback is the negative feedback. This negative feedback is going to give me a stable operation. And then we have connecting the output to the non-inverting amplifier. This is going to result into a positive feedback. This connection is undesired and is going to result into an unstable operation. And as a result, the output would be oscillating and creating an oscillating signal at the output that is not going to uh, help me, at least, and my focus of the operation amplifier. Those could be used for other applications like a comparator when I compare two signals and I would like to have an highly accelerated output reaching the maximum. But for the scope of our course, we are only interested into the negative feedback where I have my output connected to the inverting input. We're going to come to this, but before that, I just want to show you the meaning. I just want to talk about the meaning uh, of the high gain and lower gain when it comes to sacrificing or enhancing the frequency response of the op-amp. Now, this is the open loop response, the dashed line, as you can see here. This is the open loop response. This open loop response has extremely high gain, right? However, this high gain is on the cost of the frequency of operation. So if you are to compare this op-amp with the maximum frequency of operation having a flat response, you can see that it is sub 10 hertz, sub 10 hertz. So again, that depends on the application. How much is what is the frequency of operation that you're interested in? I can increase this frequency of operation. Okay, and I can increase the frequency of operation having a flat response at, as I said, at a higher frequency. So if you are to compare this point, which is the maximum frequency of my signal at this gain with this one, if this one is sub 10 hertz, this one is in the range of above 10 kilohertz, right? So what does this mean? This means if you are designing a signal, then this signal, if you're designing a circuit and this circuit is dealing with signals that are operating at the frequencies in the higher kilohertz range, then you have to sacrifice the gain. You cannot use the same gain uh, for uh, uh, for the open loop. You have to sacrifice this high gain on the cost of increasing the range of operation based on the frequency of the signals that you are designing the circuit for. Does this answer your questions? It's not damaging components, it's destroying the signal itself, distorting the signal itself, because you start having different gain levels for different frequency ranges. Okay, so this is why we tend to adjust our gain. Now we come to what's called the voltage saturation. I think we talked about this briefly when I told you that the operation amplifier cannot supply a voltage that is beyond its maximum or its minimum voltages that you are supplying. In other words, look, you can look at the operation amplifier as a device that you are supplying it with a DC voltage that is has a maximum and has a minimum. The maximum is in the positive values and the minimum is in its negative values. And then you are applying a signal at its input. So because the operational amplifier has a high input impedance, he will not withdraw high current from that signal, which means that he will not load the signal, ending ending with deteriorating or distorting that signal. So this signal will not be loaded, and this is because the operation amplifier has high input impedance. Now, what is the operation amplifier is going to do is going to look at the signal that he is sensing at its input, and he's going to replicate the signal using his own power supply that you are providing the operation amplifier for. So look at it as a device that is looking at the signal that you are providing at its input without affecting or without loading that signal, without deteriorating or distorting that signal. He is reproducing that signal again with a with a higher magnitude using the power supply, the DC power supply that you provided the operation amplifier. Look at it as if he is reproducing the signal without affecting that signal. From where? From the power supply, from the source, from the voltages, the maximum and the minimum voltage that you are giving to it. So he uses those voltages as his source of generate of operation. So the op amp is the main source. You are, however, it's a dependent source, right? It is a dependent source. He does not generate anything unless you let that signal goes, this controlling signal that he senses at the input of the op amp, and he will act upon. So we've covered the dependent sources before, and the operation amplifiers is an excellent example of a dependent source. Yes, you can look at it this way. You can look at it this way. Yes. Okay. So now to understand what does saturation mean here, let's look at those two signals. Let's assume that I have this sinusoidal signal that I am applying at the input of the operational amplifier. So here, this is my sinusoidal signal. It's a weak signal, right? And then, so this one is the VD. And now the V output is going to magnify. Let's assume that A here, the gain is resulting into a magnification something like this. It doesn't look nice. I'll try to make it better. So here, for example, so let's assume that the output should be this way, which is A VD. However, this is the VC.
Sure.
Yes,
So the smaller wave is VD, and the
the
larger one is V naught.
that's right. I just want to demonstrate the saturation. So let's assume that the output should be this way. However, my VCC is here. This is the positive VCC, and this is the negative VCC. Now, regardless of the operation amplifier topology that we're using, assume we're using an operational amplifier in a circuit that is giving me a positive output, right? With respect to the input. Now, what's going to happen when this operational amplifier, when this output, so this is V naught, this is the maximum voltage VCC. This is the minimum voltage minus VCC. Now, what's going to happen is when my signal, the output signal that is magnified, amplified, reaches the maximum voltage, it's going to be clipped. Why? Because the operation amplifier indeed cannot give me more than that value. So this one is going then go down all the way to here and then get clipped like this because he reached the saturation. So this is this is the meaning of the saturation, where your signal has reached the maximum or the minimum value where it cannot go beyond. And that's why at this saturation, it would be cut like this. It becomes like this. So in other words, the signal is going to be deteriorated because of this clipping. When do you see this in practical example? You see this if you have, let's assume you're setting up, a sound system on a stage in an event, and you are calibrating the microphone, right? Calibrating the microphone such that the sound, the voice is going to be heard everywhere in the hall. If the magnification for the microphone is so high, then you will see that the sound signal is going to be clipped. Why? Because you already reached the saturation of so the sound is not going to, the voice or the signal is not going to sound clear to you. Yes.
So, sir, the point of an op amp is basically to amplify voltage.
Right.
But why not just use a transformer then?
Why not?
Why not use a transformer?
And the transformer at the end, you have the power, you have the signal being, you're not changing, you're not adding any gain. You are changing the voltage, sacrificing the current, or changing the current, sacrificing the voltage between the prime and the secondary. So at the end, the transformer is a passive device. This operation amplifier is an active device. It has its own source that is increasing the power of the signal. It's a completely two different concepts. Here, you are amplifying the signal. You are adding power to the signal. You have a weak signal that has very very low energy signal, and then you are amplifying that signal. You're adding power to it. There are two completely different approaches. The transformer is a passive device. It has losses. You're going to end up losing some of the power through the thermal loss inside the coils. Op-amp are active devices. They provide gain. They add power to my signal. So they are the opposite of the passive devices. We don't look at the losses in the op-amp and the power amplifiers and those amplifiers, because the purpose is to add power, or sometimes, as we will see later on, we worry about the signal that we apply we don't want to load the signal, this operation amplifier is going to do all the mathematical operations that we desire on those signals without affecting the original signal.
So, sir, an op amp just it adds gain for voltage, period, whereas a transformer sacrifices current to gain voltage.
You're still at the end adding power. You are adding power.
Okay.
A voltage here, a voltage drop here is going to result into a withdrawn current from that source as well, right? As long as this op-amp is able to handle the maximum power that you are trying to withdraw from this op-amp, you are okay. Okay. Again, the input power for the op-amp are the input voltages for those op-amp are the source of energy that this op-amp is using to generate or reproduce those signals at its output. So this is just to explain to you what does what is the saturation and why the saturation is happening. Now, if I am to interpret this one in terms of so this is voltage. If I am to interpret this one into uh, VD versus V naught, the gain is going to be constant in between. So you reach to a point here where the gain is going to be constant, right? And then reaches the saturation. So what is this point? This point, just a second. Okay, so that point is the point where I reach the saturation. Look at the output. The output will be clipped. And this is the VCC. And this one is the minus VCC that we talked about. But if you want to calculate this, based on this equation, if you know the gain and you have the V naught as VCC, so VCC, see this is V saturation, this is VD saturation, then VD saturation is indeed VCC over A. So this is the point, that if you exceed at the input, definitely you're going to reach to the saturation right here. And if you want to do this, you do this for the minus VCC to get that point. That is also will be a negative point, which is minus VCC over A. Okay. So far, this is explaining what does this what's this amplifier op-amp doing? What is the purpose of this op-amp? What is the what is the concept of operation behind this op-amp? Remember, we said that ideally we will take this gain to be infinity. We will take the input impedance to be also infinity, and the output resistance to be input resistance infinity. Output resistance is zero for the ideal op-amp, which is the one that we will be dealing with. Now, since the Ri is infinity, what's going to happen? If Ri is infinity, this means there would be no withdrawn current in this input resistance. So if I go back to here and I say that this VD is Ri times Ri, then if I say this Ri is infinity, then the current going would be zero, right? So what does this mean? If the current into it would be zero, then I have here the voltage that I am calling V minus because it is at the inverting, and the voltage that I am calling here V plus would be the same, right? Why? Because now I have VD, which is a V plus minus V minus equals to zero. So because the resistance is extremely high, this voltage now becomes extremely small to an extent that I can say that both voltages are equal. I can say now both voltages are equal, and in this case, this is the second. So if my first rule in analyzing ideal op amp is there is no current. Why? Because the current I is zero. Entering into the op amp is zero. Why? Because the input impedance is so high. Ideally, it's infinity. So the current entering into it is zero. And this is going to result into VD also to be zero. So what does VD equals zero mean? VD equals zero means, so here we have the current, which is any current from either the non-inverting or from the non-inverting or from the inverting would be zero. So there will be no current withdrawn by this op amp. And because of that, VD also would be zero. What does VD equals zero it means? It means that the V non-inverting would be equal to the V inverting. So those are the two rules that we will be using to analyze the operational amplifier, ideal operation amplifier, which is the model that we will be using in this course. Rule number one, the operational amplifier is not gonna withdraw current from either input. Rule number two, the potential at the inverting will be equal to the potential at the non-inverting. Those are the two rules that we will be using in analyzing our operation amplifier circuits. Any questions so far?
Sure.
Yeah, go ahead. Repeat your question.
Okay. So on the previous page, the desaturation is where positive VCC levels off. Am I correct?
Right.
Okay. And is this what you meant by open circuit? Because an open circuit basically has infinite resistance.
That's correct.
Okay.
Here, I'm just talking in general about an operation amplifier that has an output being in phase with the input, which is basically input is positive, output is positive, and then it's eclipsed or reaching the saturation due to exceeding the maximum and the minimum gain. Right? Make sense?
Okay. Yeah. Thank you.
You're welcome. Just a second. Okay, so now let's start with the first uh, type of amplifiers, which is the inverting amplifier. So in this case, we will for the inverting amplifier, the output V naught, as you can see here, is being connected through a resistor to the inverting input. And then from this point, I have the voltage VI connected through the resistor R1. And then the non-inverting input is connected to the ground. This is what we call a negative feedback because the output is connected to the inverting input. Negative feedback. All our op-amps in the circuit that we will be looking at, they have to have a negative feedback. A positive feedback is going to result into an unstable circuit. We need a stable circuit, so it will be connected through the negative feedback. So always keep this in mind. Negative feedback. The output is connected to the inverting input. Okay. So this is how we achieve the negative feedback. This is how we achieve a stable circuit. Now, let's apply the two rules that we talked about in order to calculate the relationship between the input and the output. So my circuit here, this is the signal that I am applying right at the input. And this is the signal that I am getting right at the output. Notice that they have the same reference, right? They're connected to the same ground. And notice that V2 is connected to the reference. What does this mean? This means that V2 here, which is the V plus, so here I have V2, which is the V plus, equals to 0. Is that right? Now, also, let's look at the two rules that we have talked about earlier. The first rule is the current withdrawn by the op-amp is 0. So notice that I have here 0 ampere going into the op-amp. And I also have 0 ampere going into the non-inverting. So the op-amp is not going to withdraw any current from my circuit. So this is rule number 1. Rule number 2. VD is 0, which means that V plus equals to V minus. So here, V plus is V1. Sorry, V plus is V2. V minus is V1. And I know that V plus is 0. So all of them are 0. So look what happened here, and do this in different color. 0 volt here became 0 volt here. So this node is 0 volt. And this one equals to this. So if I am to apply KCL right at 1, so let me say here, KCL at 1, what do I get? I1 is entering, I2 is leaving, equals 0, or I1 equals to I2. What's I1? VI potential here at this node. What is the potential at this node? Remember, the other terminal of the VI is connected to the ground. So the voltage here is VI. So back to my I1. I1 is VI minus 0 over R1 equals, what is I2? I2 is 0 minus V naught 0 minus V naught over RF. Now, if you rearrange this equation such that you solve, V naught in terms of R1, RF, and RI, what you're gonna get is the following: V naught equals to minus RF over R1 VI. And this is the relationship for an inverting amplifier. So what does an inverting amplifier again means? It means that I do have a negative feedback, but the input of my signal is going into the negative input of the op amp. Where's the input signal? The input signal is VI. It is entering the negative terminal of the op amp, and that's why we call it inverting amplifier. So what are you expecting the output to be? The output will be inverted in the sign. So what is the RF over R1? This is the new gain. So now my gain here, because I have connected this amplifier this way, would be minus RF over R1. My gain has been sacrificed, right? However, now the gain is relatively designed to meet my requirement, and I have also gained in the bandwidth. So this is one of the ways to control the gain and at the same time to increase the bandwidth. But what we're gonna care about here is the gain of the operation amplifier being an inverting amplifier. Any questions so far about the inverting amplifier? I'm not sure if I'm gonna have time to. I was planning to solve the quiz after the lecture, but I'm not sure we're gonna have that time. But we will see where we can stop. Okay. So any question about the inverting amplifier? We I'm not sure about. I did post the feedback, but apparently the feedback is whatever. We'll talk about that. We'll talk about that later. We'll see what we can do about that. Okay, so this is what we have solved, and that's the gain. Okay, now let's look at this example. In this example, let's first understand what do we have here. We have an operation amplifier. Yes, it's an ideal op amp, and it is from inverting topology. Why inverting topology? Number one, it's a negative feedback. It has to be a negative feedback. Number two, it is an inverting topology, inverting amplifier. Why? Because the input signal is going to the inverting input. So if we want to apply now the two rules that we have talked about and solve for V naught, which is basically find for the relationship of V naught with respect to the input. So what are those two rules? We talked about them. No current is going to be with a draw. So this one is 0 ampere. There is no current into the op amp. And so I have I, if I want to call this one I1, and this one I2. So I1 equals to I2 equals to 0. And I have V minus equals to V plus. Right? V minus equals to V plus. What do I know about V plus? Let me make it that. Can you tell me what do I know about V plus? So this node and those nodes, I can say that they're the same, right? What do I know about V plus? And this one is the output. So this one is V naught. The blue one is 3 volt. What about the red one? What do I know about it? Let's see. Equals to 1. This is correct. So here, this one is 1 volt because the reference here. So, and this one is 1 volt as well. Right? So let's see this current. I will call this one, let me call this one I3. And this current is I4. If I apply KCL, let me call this one A. So if I say KCL at A, what do I get? I get minus I3 plus I4 equals to 0, or I3 equals to I4. What is I3? Can somebody tell me what is I3? Any volunteer? I3 is 3 minus 3 minus what? Oh, yes, 3 minus 1 over 4k. This equals to, what about I4? What about I4? I4? Any volunteer? 1 minus V naught divided by 10k. Yes.
So I3 is the current going from the 3 volt node to the 0 volt node VA.
I3 is the current going from the 3 volt to the 1 volt.
1 volt. Okay.
The node for the red is not 0 here.
So the red node is 1 volt.
It's 1.
Okay, and we
Because,
call that VA.
and we call that V minus.
So the
So
red node is minus V
no, no,
and
no,
it's
no,
one.
no, 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 no. The red node is V with a with the minus prime, right? And this one is V plus. However, the voltage here, due to this 1 volt source, is 1 volt. So V minus equals to V plus equals to 1 volt.
Okay.
So if I
Is
am,
this true for all op-amp circuits? So the V minus node is always equal to the V plus node, or is that just specifically this circuit?
that's correct. This is the second rule, Liam, in analyzing circuits with op amps. So
Okay.
always keep in mind that when you are working with op amps, let's take this topology. Let's put here. Always keep in mind that V plus equals V minus, and this is the second rule. The first rule, there would be no current entering the op amp. Make sense?
So we're always to assume I1 and I2 are always 0 and equal.
That's correct.
Okay.
So the current entering the op amp is 0. Both terminals of the op amp have the same potential. Does it make sense now? Okay. So now this is I need to rearrange this and get rid of the k. So I have 2 over 4 equals to 1 minus V naught over 10. Right? Then if I multiply by 10, so this is 1 over 2 equals to, or 10 over 2 equals to 1 minus V naught, right? Then V naught equals to 1 minus 5, and V naught is minus 4 volts. Make sense? So this is how we solve this example. Any question about the inverting amplifier before we move on to the non-inverting amplifier? No? Okay, so I think I'll stop here. I will stop here at the end of the inverting amplifier, and in next lecture we will continue the remaining topologies of the op-amp circuits. Any questions so far? Is everything clear? Okay, that's great.